Okay, so we looked at geometric sequences. So the next thing, or I suppose the next kind of logical step after that, is to look at a geometric series. So similar to arithmetic, when we had arithmetic sequences, we have arithmetic series, which is to do with sums or summations of those terms. So as opposed to maybe where we have kind of lists of terms where we're just kind of listing 2, 4, 6, 8, or so on and so forth, whatever the kind of connection is there, we're really looking more now at cases where I might have lists, but I'm more looking at kind of summations there. So in this case, this would be T1, T2 would be adding those two, T3 would be adding those three, and so on and so forth. So I'm looking at kind of those kind of sums, and smaller sums and bigger sums, and depending on how many terms I suppose I need to use here. So a geometric series is formed when we're adding the terms in a geometric sequence, so fairly straightforward. Again, the same as we had with our arithmetic, and we have a nice formula for it. Again, this would be given to you, so the formula Sn, similar again to arithmetic, the sum of the n terms is a times 1 minus or n over 1 minus or, where again a is the first term, or is the common ratio, and Sn is the sum of the first n terms. Now, one thing to note here as well is in some cases what we might see is we might see the formula written in this format, and all that's really happened there is they're multiplying the top and the bottom by a -1, a -1, and all that they're doing there is it's just to change kind of the order of the terms, particularly if we end up with a particular type of ratio, maybe where we don't want to have it kind of in that first order. So maybe if it's negative, or if it's just kind of not fitting with what we want there, even if it's positive, I suppose, and is going to be bigger than 1, then to kind of get that overall positive result, it just saves us a little bit of manipulation down the line. But you can use this one easily at all times as well. So if you want to just stick with 1, this is probably the best one to go with, because it's the format that it's given to you in. In terms of looking at derivation, it's no harm just to run through it quickly. So looking at the derivation, we kind of just consider, first of all, the sum of the first, I suppose, n terms. So write out the series. So let's just write out our series. So Sn would be a plus a or plus a or squared plus a or cubed, and so on and so forth, all the way up to n minus 1. Okay, what I want to do then is I'm going to multiply both sides by my common ratio. Okay, so I'm multiplying both sides by my common ratio, or. So or Sn is or times a plus a or squared plus a or cubed, and so on and so forth until I get to a or n. Okay, and what I'm really trying to do here to some extent is to get that a or to the power of n term, to kind of get that nth term as well included. So taking those away now, okay, taking those away is going to leave me with, if we kind of write it out here, even just to compare. And the one we're subtracting on the bottom here is going to be a or plus a or squared plus a or cubed plus a or n minus 1 plus a or to the power of n. So even just kind of by I there, we should be able to see that because we're subtracting a lot of the terms that we already have, we're only going to be left with kind of a select few number of terms here. And those terms are a and the a or to the power of n at the end then. If I factor out Sn here, I get 1 minus or, and factoring out a on this side, I get 1 plus or to the power of n. Sorry, excuse me, that should be a negative there, because we were subtracting it, of course. So we have 1 minus or to the power of n, and I can divide then to end up with the formula as we had it in the first place there, presented to us. Okay, so just a very quick derivation. It's not an awful lot of steps to it really, but just one that's, I suppose, worth kind of being aware of and worth knowing. We can prove that formula using induction, and that's included in the proof by induction notes. So if you want to kind of go check them and just make sure that you're maybe familiar with that proof and how we would prove it using our usual induction methods really. So just jumping into that, we're going to look at some examples here then of using that formula. And what we could call this, and what I've called in the examples here, is we call it a finite geometric series. And finite just means that it has an end point, I suppose. So we're only adding a certain select number of terms, and it's a finite number of terms, which I suppose suggests that we're probably going to look then at an infinite number of geometric terms or an infinite number of terms and adding those maybe in the next little bit. But let's just go with our finite series here first of all. So looking at the first example, 3 plus 6 plus 12 plus 24. So we have a nice little series going on here. We need to work out the different parts of our formula first of all. So a is going to be 3. My ratio comes from dividing the term by the previous term. So 6 divided by 3 gives me 2. I can use that then to work out Tn and Sn. So Tn is a or to the power of n minus 1. So that's 3 times 2 to the power of n minus 1. And I want to find T8. So that's 3 times 2 to the power of 8 minus 1, which is 3 times 2 to the power of 7, which is going to be 384. Looking for Sn then, so Sn is a times 1 minus or to the power of n all over 1 minus or. So that's going to be 3 times 1 minus 2 to the power of n all over 1 minus 2. I want to find S of 9. So that's going to be 3 times 1 minus 2 to the power of 9 all over 1 minus 2. And if I plug that into my calculator, work that out, I'm going to get an answer of 1533. So adding the first 9 terms of that sequence there brings me up to a total of 1533. Looking at the second example here, a is going to be a negative 2, and my ratio, same as before, divide a term by the term before it, is going to give me an answer of minus 3. And we could equally check that kind of using some of the later terms as well. So setting that up for ourselves, then Tn is going to be minus 2 times minus 3 to the power of n minus 1. So quite a similar kind of situation here with different signs going on. So no harm to see kind of how the negative plays into this as well. Let's just work out Sn or set up Sn as well. 1 minus minus 3 to the power of n all over 1 minus minus 3. Finding T8 then is going to be minus 2 times minus 3 to the power of 8 minus 1, which of course is minus 2 times minus 3 to the power of 7, which is going to be, I'll get my calculator here, so work that out. Okay, minus 2 times 1 minus minus 3 to the power of 7. Keeping my brackets here, I suppose, is going to be one of the hardest parts. And, or excuse me, went for the wrong one first. Minus 2 times minus 3 to the power of 7 is 4,374. And getting Sn then, I just had it typed in, but we'll type it in fresh again. So Sn, adding those terms, and this time I'm looking for S9. So minus 2 times 1 minus minus 3 to the power of 9 all over 1 plus 3. Is going to give me an answer of minus 9,842. Okay, so making use of all the information we have there, subbing those into the formulas, kind of the same way we would have done with arithmetic and sequences and series really. So the key thing really, just finding that initial term, finding that ratio. So a geometric series, I suppose, same as we said with the sequence, will have that same common ratio, and that's our relationship then between the consecutive terms. We use that then, I suppose, in working those out. Looking just at some summation notation, it's always good to kind of remind ourselves of these alternative notations. The best thing we could do in this case is to try and write out this sequence. So reminding ourselves of what the notation means. The big kind of E symbol is sum. It's a capital sigma. It just means sum. We start at the bottom and then read upwards. So we're starting from n equals 1 all the way up to n equals 5 of this sequence 2 times 3 to the power of n minus 1. Okay, so working out those different values, and we could use our calculator in this case. So 3 to the power of something minus 1. So we're starting with 1. So 1 minus 1, that gives me 2. The next answer would be to change that then to a 2, which is going to give me 6. Changing that then to a 3 is, changing that to a 3 is going to give me 18. Changing it to a 4 is going to give me 54. And changing it to a 5 is going to give me 162. Okay, so that's kind of as far as we're really going with our sum here, but we can kind of write it out and get a sense of what the overall sequence, if it were to continue, would be. So using that now to work out our initial term of 2 and our ratio then of 6 divided by 2, which of course is 3, we could possibly see those from this part of my summation notation. Sometimes it's kind of quite visible. Even comparing to one of the answers we had in the previous example, we might be able to just read that off straight away. But using now my overall sum formula for my series, I'm just going to sub in those values, or to the power of n, 1 minus or. I want to find the sum of the first 5 terms because I know I'm only looking at a sum of 5 terms here based on that summation notation. So 3 to the power of 5, 1 minus 3, and that's going to give me an answer of 242 in this case. Okay, adding up the first 5 terms brings me up to that 242. So let's look at an exam question, okay, quite an old exam question, 2002, and fairly straightforward, or I suppose quite kind of very similar to those examples or book questions really that we've seen there in this sort of topic. Find in terms of n the sum of the first n terms of the geometric series. So using my information here, I know that a is 3 because that's the first term. My ratio is one term divided by the previous term, so that would be a half. We could double check that if we wanted and maybe try something like 3/4 divided by 3 over 2 just to make sure that we still get that half, and we do indeed. So using my summation formula here then, we know it's a times 1 minus or to the power of n over 1 minus or. I can fill in that information first of all. N, 1 minus a half. And I want to find the first n terms, so I'm not going anywhere particular, so I don't actually have to, I suppose, sub in any value for n here. I'm keeping that quite open, but I'm going to just simplify what I have here a little bit as well. So 1 minus a half is of course a half, and that overall is going to give me 6 times 1 minus a half to the power of n. Okay, and I can't really go any further with that one there because I'm not using any particular values for n. Okay, so that is, I suppose, really running quickly through that idea of a general geometric series, and I suppose specifically a finite geometric series. So we're looking at cases where we're taking just a select number of kind of terms within that. We're only going to n terms or a specific number of terms, and in doing that, we can use this formula taking a as our first term and or as our common ratio, and we kind of have nothing else to consider. Now what we're going to look at next is an infinite series, so we'll maybe do that even just in the next video, just to keep them kind of separate, and that's going to be looking at maybe what are we going to do if we have to sum an unknown, I suppose, nearly number of terms, or continue doing these summations indefinitely or infinitely.